Where did we leave off? So we finished with Euler. Let's get a little timeline going. So here's, I'm going to say 1800. So Euler was like back here. And let's get 1900 and get 2000 on the page. So a young guy is reading all of the amazing books that Euler has written about number theory, about analysis, about differential equations, about geometry, right around here. We've already talked about him. It's Gauss. So this is Gauss. Where is Gauss located? Have we talked about his not his birthplace, but the place where he spends the majority of his academic career? Is at a place called Göttingen in Germany. And you're going to hear that name for about the next 150 years. It's only when the Nazis come to power that Göttingen and Germany in general ceases to be a world power in mathematics, in the same way that it is over this period. So Gauss, we've talked about Gauss a lot. He develops all kinds of amazing things. Yeah, let's not talk anymore about Gauss because we have lots of other people to get to. There's some other names here. I'm just going to put Cauchy's name, and an even more relevant name is Fourier. So Fourier, this is 1810. I'll just tell you in words what Fourier was up to. Fourier is, and Cauchy are French mathematicians. Fourier is interested in solving the heat equation. So Fourier, I'm going to call this 1810s, is trying to solves the so-called heat equation. Heat equation is you take an ice pop out of your freezer and you're holding it in your hand. So take ice pop. You know what an ice pop is, yeah. Out of freezer. And the heat from your hand is propagating through the ice pop and melting it. Heat from your hand propagates through the ice pop. And the question is, how? What's the function of heat as a function of time in the ice pop? And the question is how? And Fourier solves this. He solves this question by going all the way back to the Pythagoreans, and in particular to the Pythagorean music theory. So aren't we glad? Today we're going to try to wrap everything up, and you'll see the unity of mathematics across space and time and so on. So if we go all the way back to the Pythagorean music theory, I mean, for our purposes, it's Pythagorean music theory. That's not how Fourier is thinking about it. But remember, we talked about harmonics. We talked about Pythagorean music theory talks about harmonics, that sound is the result of superposition of simple waves. So Fourier is able to solve, I'll just draw some pictures. So there was like simple waves, standing waves, and this is the fundamental frequency, and then the next frequency is if you accelerate your jump rope a little bit faster, you get this standing wave, and then you get the next standing wave, so you get these sort of standing waves. And Fourier can solve the heat equation for these kinds of waves, and solves the general equation as a superposition of the harmonic waves, of the standing waves, of the harmonic waves. Okay, never mind what this means. I just want to throw some ideas into your head. But what he needs to do is add infinitely many of these waves up to get to the eventual solution. Needs to add infinitely many such waves up to get the full solution. And by the way, I should mention that already in the 1750s, so all the way back here, 1750s. This is come on. So 1750s, you have D'Alembert. I'll just drop it here aside. D'Alembert was working not on the heat equation, but on the wave equation. The wave equation is if you drop a pebble in the middle of a still pond, and you see how that wave propagates. So D'Alembert is solving the wave equation. He shows his solution to Daniel Bernouilli. Daniel Bernouilli is very interested in this, talks about this with Euler. And they basically, it's very, very similar to what Fourier does, except they say, okay, you can add up finitely many of these waves, but Euler was like, no, you can't add up infinitely many of these waves because we don't know how to make sense of that. Only allow addition of finitely many waves of these fundamental frequencies. And Fourier, he's this young guy, and maybe he's very risky, maybe he's very sloppy. For whatever reason, he says, no, you can take infinitely many ways and it's okay. He doesn't justify what he's doing. And this leaves mathematics in a bit of a pickle. By the way, this question of infinitely many versus finitely many, what the computer is doing right now as I speak is taking my voice. This is what modern signal processing is. It takes my voice, it breaks it down literally into, what Fourier does is give a method to decompose any frequency, any wave into combinations of standing waves, which means all you need to know is their amplitude and their frequency. So those are numbers. So what the computer is doing is storing those numbers, recording them, and then later, if you listen back to this lecture, what you'll be hearing is your speaker reconstructing those numbers, and you can only record finitely many numbers. So it's cutting off those very, very highest frequencies. And so this is why a lot of my friends who are music snobs prefer to listen to records, because a record is continuously, the needle, as a sound is moving through the speaker, the needle is continuously moving up and down. And so they feel like they get those higher frequencies that are being chopped off in signal processing the way Euler was doing it. And you want the full superposition of infinitely many ways, which is what you get out of records. So for those of you, do you even know what a record is? You know what a CD is? Okay, I don't know. It's a thing we used to have before we had the iPods in our pockets. Okay. So while this is all going on, it's causing crises in mathematics, because we already had crises in terms of not having foundations for calculus. Now we have to add up infinitely many functions to solve real world problems. We're trying to understand, the propagation of heat or the propagation of waves. And by the I'm going to call this 1830s, this becomes the subject of much study, in particular by Dirichlet, Jean Dirichlet, who is working in, can you guess? Gottingen. Yeah, Dirichlet is in Gottingen. And he starts making what Fourier was doing a little bit rigorous. It's made even more rigorous, let's call this 1850, by another guy named Riemann. By the way, we were talking about Euler's work on what became known as the zeta function, which eventually becomes known as the Riemann hypothesis. And I left a video for you guys to watch on the Riemann hypothesis for those of you that are interested. Whereas Riemann working Göttingen, okay? I hope you see this pattern of Gauss is like the Euler of Alexandria, is the Euclid of Alexandria, sort of anchoring. Now Alexandria is a major place, and now there's lots and lots of people that are there. So Riemann's working in Göttingen. And he understands, again, the necessity. He develops what's called the Riemann integral and proves all kinds of things about Fourier analysis. And he starts messing around with the following thing. So people are really worried about, when you add up infinitely many of these waves, do you really recover the original function or not? You took a function, you decomposed it into this signal processing way, and you put it back together. When you listen to this lecture through the speakers, are you really hearing what people sitting in the room are hearing? In the limit, if you were allowing infinitely many of these amplitudes and frequencies to be stored and transmitted. And Riemann basically says, for a restricted class of functions, namely continuous functions, he says, yes, these integrals all converge nicely, but he has this funny thing that he notices. He notices that if you're taking some integral, an integral is just an area under a curve. And if you change the function by taking one point, maybe some of you have seen this if you've been thinking about, if you are taking a class in calculus, one of the first things you learn about limits and continuity, and you just change the value of this function at one point, he notices that doesn't change the resulting integral, right? what the value of the integral is doesn't change when you change a single point. And he's really interested in what Fourier was doing when he comes up with this. So there's a young guy named Georg Cantor. So Cantor, I'm going to call this 1870s. Let's put him on the board here. So 1870s is Cantor, Georg Cantor. He is born in Prussia and studies in Vienna. So he's not in Göttingen, but he's around there. Is it Vienna? I'm doubting myself. I can't read my own handwriting. Anyway, he's a student. Oh, yeah. No, he's in Berlin. He's a student of Weierstrass, of course. Cantor is studying with Weierstrass, which is another important name. Weierstrass is really trying to make really completely rigorous. So people are getting ever more rigorous. And Cantor, so he's in, what did I say? He's in Berlin, actually, bless you. And Cantor says, actually, Riemann said I can take out 1 point. Bless you. I can change the value of 1 point without changing the integral. I think I can actually take out 2 points. And that won't change the integral either. Josie. Won't change the value of the area under the curve. Yeah, the way it works, it's a little complicated, but the way it works is that what Riemann thinks of as an integral is you chop this up into little rectangles. And when you change the value at a single point, you're changing a rectangle that becomes infinitely thin. And so in the limit of this process, the fact that you change the function at 1 point doesn't actually affect the resulting area in the end. Okay? So he says you can change at 2 points. In fact, if you can change at k points, you can change at k plus 1 points. And change at k points implies that you can change at k plus 1 points. What does that smell like? Induction, right? This is mathematical induction. Like I said, we're going to try to bring it all together now. And then he says, wait a second, that means I can just change it. Can't I change it at every single point? 1 point at a time? I'm just going to change 1 point at a time, the value of the function, make a completely different function, and the integral won't change. This is really bad. Different functions have different areas under the curve. Like, we have broken mathematics. Something's really gone terribly, terribly wrong. This is not fixed completely until 1901. So there's a guy named Lebesgue, Henri Lebesgue, in Paris, who's a student of Borel, who initiated this line of reasoning in something called measure theory, and there's something called the Lebesgue integral, which fixes this issue. But what Cantor stumbles onto is something even more powerful. He stumbles onto the nature of infinity. And this is, he has a variety of arguments for how to do it. I'll show you the argument that's given by David Hilbert. So let me put Hilbert here. He's another very, very important big name. Hilbert is working in Göttingen. Yes, just like all of these guys. He, around him in Göttingen, has a massive school. Hermann Weyl is here. I'm not even going to write these names. There's like Courant. Well, let me write some of these names. So these are some major figures. Get this out of the way. There's Weyl. Weyl moves from Göttingen to Princeton, to the Institute for Advanced Study, to Princeton. Then Courant is another big name here. He's working with Hilbert in Göttingen. He moves to NYU. Perhaps one of Hilbert's most famous students, and this is, I'm going to call this like 1930. I mean, she's around for a very long time, but so this is Noether. And she is working in Gottingen. She completely revolutionizes our understanding of algebra and physics, and has all kinds of amazing theorems. So she is also in Gottingen. She leaves Gottingen when the Nazis come to power and moves to, anybody know where she moves? Not to Princeton, but to nearby Bryn Mawr. So she ends up teaching at Bryn Mawr. And there are, anyway, there's a lot we need to talk about her. It's interesting. She's like the last of the great Göttingen people, kind of like how Hypatia was the last of the great Alexandria scientists and mathematicians. So, right. we're going to come back to this period. Let me go back to Cantor for a second. So this is like, hopefully you see Göttingen as this major center of mathematical progress. And very shortly thereafter, a lot of these people are going to be moving, you know, between New York and Pennsylvania. Centrally is right here, a place called Princeton. So let me explain to you how Cantor comes to understand this seeming paradox. So Cantor is forced by this line of reasoning to study the very nature of infinity. And it's explained beautifully by something called the Hilbert Hotel. So Hilbert's a big proponent of Cantor's ideas. So let me explain to you the Hilbert Hotel, which is not exactly, it wasn't originally Cantor's argument. And let me just show it to you and see what's going on. Okay, so here's what Hilbert imagines. This is David Hilbert, again, slightly after Cantor. What Hilbert imagines is the following hotel. So you have this big hotel, and there's infinitely many rooms, and here's room 1, and here's room 2, and here's room 3, and so on. Okay, and there's infinitely many rooms, and there's a night clerk here sitting at the desk, and there's a big sign out front that says no vacancy. Vacant. Let's see what is going on. No vacan. Is that how you spell vacancy? I think that's right. Okay. No vacancy. What does that mean? That means that if you look at the ledger, so there's a ledger at every hotel of like who's in room 1. So we have room 1, room 2, room 3, room 4, and so on. We have all these rooms. Okay. And in room 1 is person 1. There's somebody staying here. And in room 2, there's person 2. There's somebody staying there. And person 3 and person 4. Okay. Every single room is occupied, completely occupied. There's no vacancy in the hotel. Okay. It's like 9 o'clock at night. The clerk is about to close up shop for the day. And person X arrives. New car arrives. So here's a car. And person X is here. And he says, can I please have a place to stay for the night? The clerk says, buddy, can't you read? There's no vacancy. Like we have every single room is occupied. Sorry, I can't put you up. Good luck somewhere else. Professor Hilbert, who happens to be in the back, overhears the conversation and comes out and says, I'm sorry, person X, we will be able to house you. Just give me a second. And the clerk says, what do you mean you're going to be able to house him? You can't say, go to the end and take a room. Like everybody needs to know where they're staying. And every single room is occupied. What are you going to do? You got an idea, Eleanor? Brilliant. Brilliant idea. That's exactly what Professor Hilbert says. Yeah. So Hilbert gets on the loudspeaker. Hilbert says, everyone please move down. Everybody move down a room. Okay. So whoever was in, so the new ledger, watch the new ledger. Here we have room 1, room 2, room 3, room 4, and so on. Person 1 is going to move to room 2. Person 2 is going to move to room 3. Person 3 is going to move to room 4. Everybody has a room. Everybody knows exactly where they're going. And there's now room. Room 1 is available. Person X, please go to room 1. Have a good night. Thank you for your business. The clerk says, brilliant. All right. Eleanor got it. Awesome. The next night, person X leaves. Everyone can go back to their room. So this is day 2. Day 2. So the ledger is returned to the original state. 10 people arrive. The clerk says, I know what to do. Everybody move down 10 rows, okay? So the clerk is now wise to this. The clerk says, okay, so day 2, 10 people arrive. Clerk says, everybody move down 10 rooms, and I have space for you, no problem. No problem. Okay. Let's think about what this means. What this means is that 1, we had infinitely many people, and then we stuck 1 more in at the beginning. So 1 plus infinity is no bigger than infinity itself. Notice that's not the same thing as infinity plus 1. I can't say, X, go to the end of the hotel. What room am I supposed to go to? Everyone needs to know exactly what room they go to. Does that make sense? So note that this is not the same thing as infinity plus 1, because what do you mean at the end? Okay. 10 people arrive, no problem. Everybody move down 10 rooms, okay? And then everybody leaves. So now we're up to day 3. On day 3, there's not just a car with 10 people in it or a van or there's a big bus arrives. A big bus arrives. And it has infinitely many people on it. It's got person X1, person X2, person X3, and so on forever. So it's infinitely many people. Infinitely many people. The clerk can't say, can everyone slide down infinitely many slots? I need to make room. So he says, guys, I'm sorry, it's not going to work out. I can put 10 of you up. I can put 1,000 of you up. But I can't put infinitely many of you. There's no way to do it. Professor Hilbert overhears the discussion, comes out to the front, says, I'm sorry, thank you for coming. Just give me a second, I'll make some room for you and we'll seat all of you. The clerk goes, what do you mean? How are we going to do it? Yes, oh, you guys are so good. Yes, exactly right. That's exactly what he says. Professor Hilbert says, can everyone please double their room number? Please double your room number. Exactly right. So the new ledger will look like this. Room 1, room 2, room 3, room 4, room 5, room 6, and so on. And person 1 is going to go to room 2. And person 2 is going to go to room 4. And person 3 is going to go to room 6. And so on. Everybody has a room. Everybody knows exactly where to go. And now we have made all of the odd rooms available. And so person X1 can go to room 1, person X2 can go to room 3, person X3 can go to room 5, and so on. Everybody's got a place to stay. No problem. We're at full vacancy. It's all good. The clerk's just amazed by this. You guys are so good. I'm really impressed. All right. Day 4. Not one bus arrives, but 9 buses arrive. 9 buses. Buses, 1S. 1S for the plural of buses. 9 buses arrive. So we're back to everybody's back in their original room. 9 buses arrive. The clerk says, I know what to do. 9 buses arrive with infinitely many people on them. Times 10, it turns out. Yeah, that's why I made it 9. So the clerk says, person 1 goes to room 10. Person 2 goes to room 20, and so on. Then from bus 1, person X1 can go to room 1. And person X2 from bus 1 still, person X2 can go to room 11. I've made all of these rooms available. And then from bus 2, person X1 can go to room 2. And bus 2, person X13 can go to room 132. You see what's going on? So you just take the bus number and you take the person number and you multiply that number of 10s and then add what bus they're on. If they're originally there, they get a 0 at the end. If they're on bus 1, they get a 1 at the end. 1, 11, 21, 31. If they're on bus 2, they get a 2 at the end. 2, 12, 22, and so on. No problem. We can fit in 9 buses just like that. Okay. So by the way, what does this mean? This means now we're adding infinitely many people to the infinitely many people that we originally had. And that's still just as big as the size of the hotel. We did not have to increase the size of the hotel to fit everything. Cool. So if one such infinite bus arrives, no problem. If 9 of them arrive, no problem. That's like 10 times infinity. This is saying 10 times infinity, which is just infinity added to itself 10 times instead of 2 times, is infinity. No problem. Day 5. Day 5. Okay, we know how to make infinitely many rooms available. If we need to, day 5, the hotel's empty. It's the weekend, everybody clears out. The hotel's empty. Okay, so now the ledger is just R1, R2, R3. There's nobody anywhere. All the rooms are available. And instead of 9 buses with infinitely many people arriving, yes, infinitely many buses with infinitely many people on them arrive. Okay, so infinitely many buses with infinitely many people arrive. Okay, so bus 1, I'll put it here. So bus 1 has person x1, then there's person bus 1 x2, then person bus 1 x3, and bus 1 x4, and so on. And then there's bus 2 that has person x1, and bus 2 with person x2, and bus 3, I'm sorry, still bus 2 with person x3, and so on. And then there's bus 4 with person x1, bus 3 with person x1, bus 4 with person x1. Okay, there's this like giant infinite matrix of infinitely many buses. Each bus has infinitely many people on it. And the clerk says, guys, you're killing me. I can do 10 buses. I can do 1,000 buses. I can't do infinitely many buses. I'm not going to be able to stick them in. The hotel's not that big. You're asking about now infinity times infinity, not infinity plus infinity. This is infinity times infinity. Whoops. Infinity times infinity. The clerk's got a little spidey sense. The professor in? Professor Hilbert, can you come here, please? Hilbert comes out. He's like, I got infinitely many buses, infinitely many people. You got a trick for this? He's like, yeah. What do you think you do? This one's tricky. Everybody needs a unique room number. It's a 1-story hotel. Yeah. That's a good guess. That's a very good guess. He says every person is on a bus number and they're the person number in the order on that bus. But if we add those two numbers together, then we can sort everybody out. So the smallest sum is 1 plus 1 is 2. That person right here goes to room 1. Bus 1, x1, person 1. Of course, that's the first person you're going to put in room 1. Then the sum of 1 plus 2 is 3. Who are all the people that have a sum of 3? Bus 1, x2 has it. Bus 2, x1 has it. So these are the people we're putting next. Okay? Bus 1, x2 goes next. Then bus 2, x1. So we're going like this, down these anti-diagonals. Then all the people whose sum is 4. That's these people. This gets room 4, room 5, room 6, room 7, room 8, room 9. Everybody's going to get a seat. If you want to, you can write a formula based on the bus number and the person number for where they go. There's no problem placing every single person on from all of the infinitely many buses into the hotel. Question there, or just stretching? Is that cool? So infinity times infinity is no bigger than infinity itself. We can fit all of these people in the hotel. How cool is that? It's day 6. We're about to get to the Sabbath. In the first 6 days, God created infinity. It's day 6. The hotel is again empty. Okay, the registrar, what's it called? It's like a register. I had a different word for it. The ledger, thank you. Can't think. The ledger is just the room numbers. There's nobody there. One bus shows up. One big bus shows up. One bus arrives. It's from Sweden. They're rocking out to ABBA. They love ABBA. And it has infinitely many people on it. But it's a very, very, very large bus. On this bus, every person on this bus has an infinitely long name. Has an infinitely long name using only the letters A and B. Using only letters A and B. So one person's name, so one person is A forever. Okay? And another person is B forever. And another is ABBA, 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 BBA, and so on forever. They don't have to be periodic. They can be any, another is A, B, B, blah, I'm just going to type random letters and whatever. Okay. Moreover, every such infinite string of A's and B's, infinite string of A's and B's, is the name of some unique person on this bus. Not only does everyone have an infinitely long name, but any infinitely long sequence of A's and B's you can write down is the name of someone on the bus. Okay? You give me any sequence of A's and B's, that is someone who's on that bus. They show up. The clerk says, you know what? I have no idea. I got this professor here. He'll figure this out, I'm sure. Hilbert, please help. Hilbert says, can't do it. Sorry, guys. Can't do it. The clerk says, what do you mean you can't do it? You showed me all this wizardry with all these amazing things you've been doing with infinity. Yeah, you got infinitely many buses with infinitely many people. This is just one bus. What's the problem? That's true. That's already a problem from the very beginning because the ledger has to have R1 through R infinity. I mean, yeah, now we need a really long ledger this way. You have to suspend your disbelief about all of the physics involved here. Layla?
It's qualitative and not quantitative.
Yes. There's a way that we can make this precise. So let me try. Yeah,
So, like, it feels like variables versus like rational numbers, if that makes sense.
you're very, very close. You're really, you almost put your finger right on it. Let me show you, Alexandra.
Same way, shifting people from one room to another or 10 rooms.
Yeah,
It's
that's,
just like patterns.
you guys are right on it. In fact, the word that you said, there's not like an order to it. How do you figure out?
It's not going to be an alphabetical order theoretically because there's like A and that's S first and then A dash. Well, but no, but then it's infinite.
That's it. What's the next
You can't
one?
go to the end. It's impossible to figure that out, right? Because it has to be A infinity plus 1B.
So the most natural thing would be just have everybody line up in order, let's say in alphabetical order. And I'll give you guys a room in order. The first one's A. Sure, no problem. Who's next? Where's the B go? At infinity? You can't do that. Specify the name. The second you specify who this, but okay, fine. So we can't do it alphabetical. It doesn't matter. Let's imagine that we did. Imagine that we successfully housed everyone. Then what would the ledger look like? The ledger would be something like this. Okay, here's room 1. We're assuming that every single person on the bus has a unique room. And we're going to find a contradiction. So here's room 1, here's room 2, here's room 3, here's room 4, here's room 5. Okay, and as you said, now the paper needs to be infinitely long that way in addition to infinitely long that way. But okay, again, suspend your disbelief. So let's say in room 1 we're going to put A. Okay, that's that person's name. In room 2, they don't have to be, there's no such thing as alphabetical order. But what order can we give them? How about all B's? Fine, I know that guy. Hey, B, how you doing? Yeah, everything good? How's the family? A, B, B, A. ABBA can be next. A, B, B, A. You see why I like to call this ABBA. Then whatever. Somebody shout out some letters. A, great. B, 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 A. Love it. Thank you. How about one more? Here, I'll just make something up. Hopefully you see that I'm just putting in random letters, random sequences. As long as I don't write the same sequence twice, no one's going to get 2 rooms, right? Where space is at a premium. So Professor Hilbert says, imagine we successfully housed everybody. There's this infinite long ledger. Every single person has a place to stay. I claim you've left somebody out. You've left infinitely many people out, but if I can show you that you've left at least one person out, the whole thing is done. Here's who you've left out. You left the following person off the list. Off the list, this person has nowhere to stay. I'm going to go to room 1, and I'm going to look at letter 1, and that's an A. If I change that letter, then of course this person, the person whose letter starts with a B, is not in room 1. So whatever else happens, this person is not in room 1. I'm going to go to room 2, and I look at the ledger, and I say, what's the second letter? It's a B. So I'm going to put an A here. That person, because it differs, whatever this name is, differs from the name at room 2 in the second letter. So this person is not in room 2. Then room 3 has a B in it, so I'm going to put an A there. Room 4 has a B in it, so I'm going to put an A there. Room 5, 1, 2, 3, 4, 5, has a B in it, so I'm going to put an A there. And this person is not in room 1, is not in room 2, not in room 3, not in any of the rooms. You have not housed this person. And even if you try to house this person, I'm just going to run the argument again. There is no way to get all of the people on that bus into that hotel. This is called Cantor's diagonal argument. You see why? This is called Cantor diagonalization. How wild is that? So how big is this bus? Let's think about how big this bus is in terms of course, it's infinitely large, but let's think about what if we had, how about just if instead of infinitely long names, what if the names were length 3? How large is the set of all names in 3 letters? Names of length 3 letters in A's and B's. Okay, so there's AAA. Now we can do it alphabetically. Then it's, what's the next one? It's only 3 letters. AAB, then ABA, then ABB comes first, then BAA, then BAB, then BBA, then BBB, and that's it, right? I think we got everybody. How many is that? 1, 2, 3, 4, 5, 6, 7, 8. That's 8 people. Why is it 8? Good guess. This is the one time there's only one pair of numbers that satisfies 2 to the n is equal to 3 to the m minus 1. There's only, in fact, one pair of powers that differs by 1, which is 8 and 9. That's a major theorem that we're not going to talk about. There's another reason why it's 8. It's not because it's 3 squared minus 1. It's because it's 2 cubed. I don't know who said that. Why 2 cubed? The first letter could be an A or a B. You have 2 possibilities. The next letter could be an A or a B. That's 2 more possibilities. The next letter could be an A or a B. That's 2 more possibilities. So you have 2 choices for the first letter, 2 for the second, 2 for the third. That's 2 times 2 times 2 choices, 8. Does that make sense? If we had 10 letters to play with, the number of names would be 2 to the 10. Does everybody see that? 2 to the 10, which has to be 1,024. If you know that number, doesn't matter. Okay. So how big is the bus? Yes, exactly. So the size of the bus, the number of elements on the bus, we should think of as 2 to the infinity. Because we can choose, because we can choose an A or B, but we get to choose it infinitely often. And what we just showed is that 2 to the infinity is strictly larger than infinity. And now we have to be actually much more careful with what I mean by this symbol. This symbol no longer makes any sense. Okay, so by infinity, what I really originally meant was what's called countable infinity, exactly as Alexandra pointed to. Countable infinity. And there are other infinities that are uncountable. And this is some kind of uncountable. Countable means we can place them in an order. And this is an uncountable infinity. So we have to be, I can't just write the symbol infinity. Which one do I mean? In fact, there are infinitely many kinds of infinities. That's going to take us really far afield. So Cantor starts messing with this stuff. And in 1874, you see, it's not that he's trying to do something weird. He single-handedly invents this theory of ordinals, what we call ordinals and cardinals. In 1874, I guess I'll put it right here, he realizes that this silly little counting thing has a dramatic consequence. Think about the rational numbers. Which kind of infinity is the rational numbers? Is it countable or uncountable? Could we order before we do the rational numbers, how about the integers? The integers, right? If I were to write the integers in order, I would say 0, 1, 2, 3, 4. That part, of course, I can put those people in a room. How would I put these people in a room? -1, -2, -3. How would I reorder this so that it's not doubly infinite? This is like infinity plus infinity, the positive integers and the negative integers. I can reorder that by saying, exactly, let's order them by the absolute value. Awesome. So we have 0, that's the smallest one. Then we've got 1 and -1. Those have absolute value 1. Then we've got 2 and -2. Then we've got 3 and -3. 4 and -4. We have moved all of the positive numbers, doubled their size, and left room at the odd spaces for the negative number. Okay, so the integers are countable. They're of the same kind of infinity as Hilbert's hotel. These are countable. How about the rational numbers? Rational numbers look like, I mean, how do I even write down what a rational number? I can't write it in an order like this, but I can write the rational numbers like this. I can write 0, and then all the things that have denominator 1. So here's all possible integers. I'll write it like this: 0 over 1, 1 over 1, 2 over 1, 3 over 1. Over here is -1 over 1. Over there is -2 over 1, and so on. And then I can think about all the things that have denominator 2. This is 1 over 2, 2 over 2. Now, 2 over 2 we already have. 2 over 2 is the same thing as 1 over 1. So we don't need to find another place for this. 3 over 2, and so on. And here's 0 again. 0, we don't need an extra place for 0. This is 0 over 2. -1/2. -3/2. We don't need right? And then we've got a third. And -1/3. This is -1/3. Here's +1/3. Here's 2/3. Here's 3/3. I don't need that. 4/3. Okay, I have this list, and I have this infinitely long list depending on the size of the denominator. What is this? Infinitely many buses with infinitely many people on them. Is this countable? Yeah, we can line them up. First, we line up, instead of writing it like this, what we should do is 1, -1, 2, -2, 3, -3. Right? We already know how to do that, so that everybody lines up in one direction. And then we do that snaking argument. We do that diagonal, and we'll get through all the rational numbers exactly as we did before. Right. There's one more that I want to talk about. So the rational numbers are in fact countable. Do you remember when we were talking about the 3 unsolvable problems, the big 3 from ancient geometry? The last one was squaring the circle. And we were talking about squaring the circle. We talked about the real numbers. And we talked about the rational numbers inside the real numbers. And then there were the algebraic numbers. The algebraic numbers, Q bar is algebraic numbers. they actually have to leave the real numbers for that because actually all rationals are algebraic. So this is the algebraic numbers, Q bar. They are numbers that are solutions to polynomials with, somebody said, I heard somebody say it. Yes, integer coefficients. These are solutions to polynomials with integer coefficients. Okay, numbers like, if I write 4x to the 7 minus 3x to the 5 plus 12x minus 3, that's a polynomial. It's degree 7. The degree is right here. So this is degree 7 polynomial. It has integer coefficients. 4, -3, 12, and -3 are all integer coefficients. And any of the roots of this polynomial, any potential real roots of this polynomial or complex roots of the polynomial will be algebraic numbers. Places where the polynomial is 0. That's what Q bar is, algebraic number. Sometimes they're complex, like x squared plus 1 will have not real. The root of x squared plus 1 is I and negative I. We have complex numbers. But all rational numbers are algebraic. What about the set of algebraic numbers? Countable or uncountable?
Not like that, but with the coefficients from these coefficients like going.
Yes. How do we order the algebraic numbers? How do we order polynomials? Yes. You guys got it. You guys totally got it. Order the polynomials by degree. Order polynomials by degree. So now the bus 1 is linear polynomials. Bus 0 is a constant polynomial. That's just the integers themselves. Bus 1 is degree 1 polynomials. Bus 2 is degree 2 polynomials. In each degree, once we know what the degree is, we can order things in the same way that we ordered those finitely many sequences of infinities. Order polynomials by degree, then by the previous methods. So algebraic numbers, the infinitude of the algebraic numbers is countable, can fit into Hilbert's hotel, is countable. How about the real numbers? What about real numbers? The real numbers, in particular, contain all the numbers in the unit interval, right? Just from 0 to 1. And the numbers in the unit interval, in particular, contain all the numbers that look like this, 0.1111111 forever. And they contain the number 0.2222222 forever. And they contain the point ABBA, 1221, 1221 forever. And they contain the point 0.121121111. Exactly. So this infinity, the set of numbers between 0 and 1 that only have 1s and 2s in their decimal expansion, is already uncountable. Uncountable. Way too big. Uncountable. That infinity is way bigger than the infinity of the integers and of the natural numbers and of the rational numbers and of the algebraic numbers. Of course, the entire interval 0, 1 is then therefore also completely uncountable. Therefore, the real numbers themselves are completely uncountable. Therefore, this is Cantor's conclusion. Not only do transcendental numbers exist, but they're the vast majority of numbers. Therefore, transcendental numbers are numbers that are not algebraic, real numbers that are not algebraic. Transcendental numbers not only exist, but are the vast majority of all real numbers. because the algebraic numbers are this tiny, tiny infinity that's infinitely smaller than the infinitude of the real numbers. So this picture is the transcendental numbers are out here. These are the transcendental numbers. This picture is a gross negligence of the truth. The truth is that you can't even see the algebraic numbers. It's this sea of real numbers, and the algebraic numbers, never mind the rational numbers, are this tiny, tiny little speck of dust. What's significant about this result, and what's significant about the fact that it happens in 1874? So in 1874, Cantor, by the way, no relation that I know of. Kontorovich is the same thing, son of Cantor. Cantor proves that there are infinitely many transcendental numbers. In fact, most numbers are transcendental. Is there a number anyone's particularly interested in? Which happens when? Do you guys remember? Or who did it? 1882. 1882. Right here, 1882 is when Lindemann proves that pi is not algebraic. Pi is transcendental. And just before that, Hermite proves that E is transcendental. For the first time, in my reading of this, Cantor's work reinvigorates research into transcendence and gets Hermite to prove that E is transcendental, gets Lindemann to prove that pi is transcendental, and resolves a 2,000-year-old problem in geometry of whether you can square a circle or not. Yes. Let me write it down. So, let me just say it again. Cantor's work, I don't know that this is really the case, but in my reading of this, Cantor's work invigorates, is that close enough? That's right. Reinvigorates research into transcendence. And shortly thereafter, Hermite proves that E, remember E to the X, this Euler number, E is transcendental. And so this is Cantor's work is 1874, and 1882 is where Lindemann proves that pi is transcendental, resolving the 2,000-year-old problem of, I see, I'm running out of room. 2,000-year-old problem of whether you can square the circle. So if we hadn't studied those geometric problems in the depth that we did, we would not appreciate the significance of what Cantor's discovery, and then Lindemann's, of course, eventual, if he really was motivated by this, which it seems to me reasonable to be the case, resolution of this geometry problem through infinity, through this crazy study of infinity. Do you think Cantor was celebrated as this great genius who invented this really single-handedly? This is one of the rare instances of someone completely out of nowhere, there's no precedent for this, single-handedly developed this entire theory. Argus? Yeah, a whole lot of people immediately dumped on him. This is not mathematics. This is some kind of garbage, gobbledygook. This makes no sense. He shouldn't even be allowed to work here. If he tried to give a lecture, they would stand outside with signs saying, you know, no Cantor on my campus. No, that's not what happened. But so many famous people, Kronecker most famously, many famous people hated this and tried to shout it down. Okay, Kronecker in particular, I'll just put his name there. A very famous mathematician. Eventually, people came to appreciate what Cantor was doing, and in particular, he had a very big proponent in David Hilbert. So Hilbert is the one that said, no one will remove us from the paradise that Cantor has created through our understanding of infinity. Eventually, Cantor was supported by Hilbert, among others, and is now revered. Does this ring a bell? Hippasus, exactly. right? This is just like Hippasus, you know, think back to Hippasus. Think back to Hippasus. Think back to Gauss himself. Not that he, Gauss is that he was afraid to reveal his research into non-Euclidean geometry, fearing ridicule, fearing the cancellation that would come. Gauss withholding his research on non-Euclidean geometry, fearing ridicule. You know, it's always these young people that don't know any better. Like Cantor didn't know any better. He didn't have anything to lose by coming out with this theory. And the people who were doing very advanced, serious mathematics said, no, this is bunk. And it takes a later generation, someone like Hilbert, to come along and say, no, actually, this is beautiful and amazing stuff. This has even more consequence. Yeah.
Euler's constant transcendental.
Euler's constant is transcendental, yes. So this is E right here. And that's what Hermite proved shortly before Lindemann proved pi. By the way that Lindemann proves that pi is transcendental, let me just throw this in here. Aside, a crucial ingredient to go from E is transcendental to pi is, does anybody know? Here's the crucial ingredient. Is this relationship between E and pi that we saw last time in Euler's identity. Okay, that's a crucial ingredient in this proof. We're not going to go over the proof. It's a little too complicated for right now. Okay, so do you see the unity across space-time of every, like, had we not had all of these previous conversations, what I'm saying now wouldn't make any sense. Right? So we're really finally starting to put everything together. Now, we started the entire semester with an understanding of what mathematical epistemology is. How do we understand what is or isn't truth? And we have the axiomatic method, and we have, you know, rigorous deduction from first principles, and that's what we believe to be true. And Hilbert, so now we're in like 1900. We're back to Hilbert over here, and Hilbert says basically, let's really get the axiomatic method perfect. This is like the Industrial Revolution. So Hilbert imagines a machine that you just crank like this all day long, and it starts with the axioms and it spits out theorems. Okay, maybe theorem proving should become mechanical. So this is Hilbert's dream, let's say. Hilbert's dream is that theorem proving can become mechanical. He imagines a machine. Imagine a machine that you crank, and it starts with the axioms, and it makes all possible logical inference moves. Starts with the axioms, makes all possible logical inferences, and as a result proves all true theorems, and hence proves all true theorems. We don't have to do anything anymore. We just sit back and, you know, let the thing run. That's the job of a mathematician, is to sit there. A mathematician is one who stands at the crank and does this for 8 hours, and then, okay, it's your turn, you know, I'm going to take a rest, and that's it. This may still come to pass, depending on what happens with the AI over the next 10 years. But so what he imagines, first of all, our axioms need to be consistent. Axioms are consistent, so they don't prove false theorems. The only thing that you can reach, the only theorems that you can reach from these axioms are actually true. No falsehoods. Can you think of a falsehood, an axiomatic system that leads to a falsehood? The Pythagoreans, the axiom of commensurability. He knows that story. He says, let's not have that. Let's have only axioms that do not reach falsehoods. No, like axiom of commensurability. See, it's all coming together. So that's one thing he imagines. The axioms are consistent. And another thing he imagines is they're complete. The axioms are complete. So any true theorem has a proof within this axiomatic framework. Within this axiomatic framework. right? That would be the dream. The dream is you stand there at the crank, it spits out theorems, logically derived from the axioms. It does not spit out any theorems that are false. Hopefully the axioms that we come up with are good enough. We're not going to fall into the trap of the Pythagoreans. Moreover, if we just stand there and spin long enough, it will produce every single theorem that's actually true. Like a computer. This is before the age of modern computers. By the way, another person I should add to this list of famous people in Göttingen is Johnny von Neumann. How did I miss von Neumann? Another very famous person here is von Neumann, the inventor of the modern, well, okay, Turing also, Turing's going to appear here in a second. Turing studied in Cambridge. He spent a little bit of time in Princeton and hated it here and left. Von Neumann was in Gottingen and moved to Princeton, right over here at the Institute. So Gottingen to Princeton. There's a big pipeline from Gottingen to Princeton. Another German to Princeton. I mean, I don't know why I missed Einstein. Okay, that's another person. He didn't come from Göttingen, but and he wasn't actually German, Austrian or something. Whatever. Einstein moves to Princeton. But the person we need to talk about before Turing is our last famed person, which is Kurt Gödel. So Gödel also, by the way, moves to Gödel is Viennese, if I recall. Prussian? I should know this. Wait a second. Yeah, I think Gödel is from, anyway, he moves to Princeton. Viennese. He's in Vienna. Gödel, another young guy, comes along and says the following. He's trying to understand this dream of Hilbert's. Okay? So this is Kurt Gödel. Again, eventually he moves to the Institute for Advanced Study here in Princeton. And Gödel starts thinking about what is a theorem. Let's think about what a proof of a theorem is. What is the proof of the theorem? What really is the proof of a theorem? Like, you know, what's a statement of a theorem? It's like a statement looks like there exists a number n so that for all whatever, so that for all yada yada. Let's not even say what it is. Let's not even say the statement, right? There exists a number so that yada yada, and then for all numbers this happens. Like that's what a statement looks like. Statements, all statements in mathematics, every single theorem that has ever been proved has been written down, is written down using finitely many characters. And in fact, we can just think of not just characters, but zeros and ones, because those characters are converted into ASCII. The characters really are converted into, this is long before, this was really revolutionary at the time because people didn't have computers. Now you can very easily imagine that there's no difference between a theorem and a number. Theorems are themselves numbers. Statements are themselves numbers, and proofs are themselves numbers. So ASCII, what's ASCII, right? It's a number. It's zeros and ones. It's binary. You can think of those zeros. This is converted into binary, zeros and ones, which means you can represent that sequence of zeros and ones. Any state of my hard drive has a finite list of zeros and ones, and whatever state it's in right now can be represented by a series of zeros and ones, which means it's just a number. Okay? Which is just a number. A number. Right? And a proof is also written in language, and a proof is also a number. So when you say a statement is provable or a statement is not provable, to say that a statement is not provable means that there does not exist number n which proves that statement. Right? If I want to say something's not provable, the way to say it is there does not exist a number n, which if you unpack the meaning of that number, we've given numbers meaning. Numbers can be zeros and ones representing the state of a hard drive, where in the hard drive is a text that has the proof of a theorem with logical inference in it. So far, so good. This is going to get a little deep, but we're almost there. Sure. Yeah. What I'm saying, yeah. Tell me what you have followed so far. Oh, ASCII. Sorry. ASCII is the standard, like when you write the letter A on the screen, the thing that the computer is storing is 113, making up that number. ASCII is like the digits from 000 to 999 have all been converted into symbols. And so when I write a little lowercase a is like 100 and capital A is like 200 and B, so numbers are being, letters and symbols are being converted to numbers. Yes. Yes.
Why was he about text as like
Yeah, because even formal mathematics is text. There exists a symbol. X is a variable. If you want more variables, you can do x prime, x double prime, x triple prime. He basically realized that every statement in mathematics is a statement in text. Algebra has one, is a statement in text. Text can be converted. There's only finitely many possible symbols to be used. If we use 000 through 999, we'll get all the numbers. If we concatenate those numbers together, we get all possible statements. Most numbers do not represent anything, have no meaning whatsoever. But some numbers will represent a proof. Have I gotten you closer to understanding what this is saying?
What are symbols like triangles?
Yeah.
Or like circles?
Yeah.
And still turn those into digits?
Yeah. Right? There is an ASCII symbol for circle. I don't know what it is. Yeah, let me not try to Google it right now. No, I'm making up the term. ASCII is like for us to talk about what he's doing. No, he just said every symbol can be represented by a number, and when you concatenate those numbers, you get other numbers, and those numbers can have meaning sometimes. And so to say that something has a proof means that something has there does not exist a number n which proves, let's say, statement x for any statement. Here's the rub. This statement, the previous statement, the thing in quotes, is itself a statement. It has a variable. X is the variable. It has is itself a statement with a variable x. I'll give you yeah. Should I give you the simple version of this? Let me finish with the sentence and then I'll say what it means. With a variable, that statement itself has a number. That statement itself has a corresponding number, let's say y, and then you apply the statement to the number y. Okay, this is not going to be understandable. Let me give you a completely unrelated thing. Okay, totally unrelated. Okay, there's a town. And the town has one barber. And the barber cuts everybody's hair, except for the people who cut their own hair. Some people cut their own hair. Some people cut their own hair. Some go to the barber. You know where I'm going with this. Who cuts the barber's hair? Who cuts the barber's hair? So, well, let me, there's one more sentence I have to add. Anyone who does not cut their own hair goes to the barber. And anyone who goes to the barber, of course, doesn't cut their own hair, and vice versa. Who cuts the barber's hair? If the barber cuts his own hair, he can't go to the barber. Okay. Everyone in town gets their hair cut in the town. Okay. Let me give you another one. Here, I'm just going to say this statement, I myself, this statement is false. Okay. Tell me about that statement. Is it true or false? This self-referential statement. a statement that refers to itself, is false. If it's true, then it's false. If it's false, then it's true. Who cares, right? This is some stupid game. You guys know this riddle. You come to a fork in the road, and there's two people standing there, and you know that one of them always tells the truth and the other one always lies. You only get to ask one question, and you want to know which way to go. Exactly. Exactly. What would the other person say? If you're talking to the liar, the other person will tell you the right way to go. The liar will switch it and tell you the wrong way to go. If you're talking to the honest person will honestly tell you that the liar would tell you the wrong way to go. So whatever the answer is, you always do the opposite. Okay? You can get information out of this. So this is an instance of that. What Godel does, Godel creates, through the process I described above, but maybe it's a little bit too complicated, creates the statement, this statement has no proof. It's the analog of this statement is false. By converting things into numbers and doing the Cantor diagonal argument where you feed something into itself. It's not really Cantor diagonalization, but it's closely related. This statement has no proof. If it genuinely has no proof, then it is a true statement. That's unprovable. Your system is incomplete. If it's a statement that is provable, then it's a false statement. Your system is inconsistent. Godel destroys Hilbert's dream. You do not have a right to knowledge. Not in this world, not even in mathematics, not even in this restricted place of mathematics. So having constructed this, so if this statement it's a statement in the theory, can indeed be proved from the axioms of the theory, then the statement is false. And the theory is inconsistent. It's like the axiom of commensurability. You've proved a false statement. That's bad. And the theory is inconsistent. Okay? If the statement's true, then there's a true statement in your theory that has no proof. Then there are true statements that have no proof. And your theory is incomplete. Completeness is that we can prove any true statement is incomplete. This destroys Hilbert's dream. We do not have a right to knowledge. All this stuff that we've been working up this entire semester about the beauty of the axiomatic method, the mechanism by which we're going to arrive to absolute truths, is limited, is itself limited. There is no axiomatic system that's powerful enough to do basic number theory, because you need number theory to be able to speak about numbers, turn ASCII and so on, that will prove every true statement or will ensure that the only statements that are proved are indeed true. So every time you learn something, you should cherish it. All right. Thank you for your time. It's been a pleasure.